In this lesson, we're going to talk about writing exponential functions that can help us model real-world situations. And we're going to use the key features that we talked about in a previous lesson to analyze and break down what this stuff means in terms of our equations. And so we talked about in the last lesson, we've got exponential growth functions and exponential decay functions. So we're going to talk about growth first. Exponential growth, remember, happens when we have a value that's increasing and usually over time. So some keywords that we're going to be looking for when we're dealing with these word problems is that it's increasing, it grows, it appreciates. That's going to be a growth word. And so this is going to be kind of the formula that we use to write our exponential functions. So A is going to be my starting value. Okay, so whatever we're starting with, that's A. A is also going to be the y-intercept, because that's where we're going to be starting our graph from, the y-intercept. Now inside the parentheses, we're going to have 1 plus a rate, which is r. So it's going to be rate, and usually the rate is going to be some sort of percentage because we're going to be increasing a percentage over time. So let's say usually a percent. And then t is going to be our time, which is also kind of our x value, our independent variable that we're going to be raising to the as the exponent. Okay, so let's apply this. Let's look at an actual example. So this says a website has 10,000 registered users in 2012. The number of members y increases by 20% each year. So let's write an exponential function that we can use to model this. So exponential function, let's write y equals. And here we can just write up here, we have y equals a times 1 plus r to the t. And that's for growth. So since we're increasing, we know that that's going to tell us to be a growth. And so my starting value, which is my a, we know that we're starting with 10,000 registered users. So I'm going to write 10 and then 3 zeros. And that's going to be my a value. And now I have 1 plus. My rate is going to be this 20%. But anytime we're working with percents, we need to convert this to a decimal. And we do that by taking the decimal that we have and moving it over to the left 2 spaces. So in this case, 20% is going to become 0.20. And we're going to raise this to t because we want it after t years. Now we can clean up this inside a little bit. 1 plus 0.20 is just going to be 1.2 really. So it's y equals 10,000 times 1.2 raised to the t. And the t can change depending on how many years we want. So we want to know what is the y-intercept of this function. Well, we talked about on the last slide that our starting value is always going to be our y-intercept. So if we write it as a point, we can say 0 and then 10,000 because my y-intercept is wherever x is equal to 0. If you're not sure though, you can always use Desmos and plug that in. So I'll hop over to Desmos. Let's type in our equation. We've got y equals 10,000 times, we could type it in as 1 plus 0.2 raised to the x. Oops, raised to the x. Or we could type it in, our cleaned up version. One more, 1.2. And just remember that x and y are graphing letters in Desmos, where all the other letters like t are for like numbers. And so I get a picture of the graph here, and I'm going to zoom way out and up. And I can see I get this gray dot again. My y-intercept is 0, 10,000. So let's do our third question here. We want to know how many registered users will there be in the year 2020, and we want to round our answer to the nearest 1,000. And so when we're thinking about this, let's remember that t was the number of years after 2012. Okay, So to find this, we can say 2020 minus 2012. That's 8, so 8 years after. So that means my t value, or my x value, is going to be 8. So we need to write in y equals 10,000 times 1.2 now to the 8. Now we can solve this. We can figure out what this is in Desmos if we wanted to. So we could type in my equation, or we could just say, well, let's just do 10,000 times 1.2. This is going to be raised to the 8th power, and we get 42,998. So to round it to the nearest thousand, that would be 43,000-ish. And I guess I can do these squiggly lines to say we're about 43,000. There's a couple other ways that we could do this, though. We could even click on the table and think back to our function notation lesson. I want to know what this is when it's 8, and I see I get the same answer. And so that's just another way that you could think about doing this. We can change the input and say we want 8 years after 2012, and we get the same answer like that. Maybe this might be a more efficient way to do it so that you don't have to worry about typing anything in wrong because you already typed it in once. Okay, so that's just some ways to do growth. Now let's talk about decay. And so decay is almost the same thing, but now we're decreasing over time. And so we're thinking decreases, loses, or depreciates instead of appreciates. And the equation is almost the exact same, except this time I have a negative instead of a positive. So A is still going to be my starting value, or y-intercept. Okay. R is still going to be my rate, and we're looking for a percentage. And t is still going to be my time, but I know I need to subtract 1 minus my rate this time. That's the only thing that's going to be different. Okay. So let's look at an example. The value of a car is 35,000, and it loses 10% of its value each year. So I've got this word loses, so that tells me it's a decay. So I'm going to have y equals a times 1 minus r raised to the t. And so we want to write a function that tells the value of the car, vt, after t years. So this problem is telling me instead of y, I want to use v of t, which is, again, the same thing as y. And now let's think. My starting value, my a, well, the car originally costs 35,000. Now I'm going to have 1 minus this time, since we're losing, 10%. So again, I need to take my decimal and move it over 1, 2. So I'm going to have 0.10 raised to the t to represent t years. And so this time we want to know what is the asymptote. So I'm going to switch back over to Desmos now, and let's clear all of this out. And so let's plug in my equation. So I'm going to say y equals, instead of the vt, because I want a graph, 35,000, and this is 1 minus 0.1, and it's going to be raised to the x. And so let's try and find a good value here. So again, we see this time we're decreasing. And we want to know what the asymptote of the function is. So I'm looking, where does this graph look like it's stopping at? And it looks like I'm never actually getting, I'm never actually touching 0, but I am getting really close. So that means the asymptote, that means the asymptote is y equals 0. And that kind of makes sense because a car is never going to lose value. It's never going to be worth negative dollars, right? So I have to have that asymptote in place because the car is always going to be worth something, right? And we want to know how many years until the car is worth $11,000. And so in this case, we have a value. We have 11,000. So that's going to be my y. And I can figure out how many years have passed by solving for x. And I can do that if I say y equals 11,000 11,000, okay? I get this line, I get this red line that's going to be way up here. Get this red line here, and it's crossing my black graph that I had. And so when they cross each other, I get this gray point, and so I see my y value is 11,000, and the x value tells me how many years have passed. So I see that it's 10.986, so I can say maybe about 11 years until the car is worth $11,000. And so this has been our lesson over writing exponential functions and applying it to real-world situations. Exponential functions are really great for modeling growth with percentage or decay with the percentage. And we can do a lot of things if we plug it into Desmos, and we can find all the key features and just find all of the key features, but this time we're applying it and seeing what they mean in terms of a real-world situation. So I hope you had as much fun as I did in this lesson. Good luck in your practice, and I'll see you in the next video.